Here we go. We are going over the midterm 2 information or midterm 2 related questions for the fall 2018 final for MA 265. And this is actually a little bit of a scattered order that they have. We have an eigenvector question as question 3 in the final, which is not very normal. So suppose that 213 is an eigenvector of the transformation encoded by this matrix here. What is this value A? So an important geometric thing to recognize about an eigenvector is that along an eigenvector, values only get scaled by an eigenvalue, or vectors. So if we had an original vector along an eigenvector here, and the eigenvalue associated with that with this eigenvector is -1, this would be our initial vector. Our final vector would be multiplied by that factor of -1. So we can use this to our advantage, and instead of expanding all of this out and trying to factor a 4th degree polynomial to try to find the eigenvalues and then go through and find all the eigenvectors, what we can do instead is just say 2, 1, 1, 1, 2, 0, A, 5, 1, and we can essentially plug in the point or the vector 2, 1, 3. And if that is an eigenvector, what we should see when we apply this transformation matrix to this vector, that our result is scaled by a certain factor, and that will allow us to solve for A. So our first component here will be 2 times 2, 4, 5, 6, 7, 8. Our second component, multiplying our second row by the first column, there will be 2, 3, 4, and our final will be 2A plus 8. And we see that they weren't lying to us. We already knew that this was an eigenvector, and along this eigenvector we see that the eigenvalue lambda associated with this eigenvector is 4. Our first component was scaled by a factor of 4. Our second component was scaled by a factor of 4. So our third component must also be scaled by a factor of 4. So we can set 12, 3 times 4, equal to 2A plus 8. That is 2A equals 4, or A equals 2. So 3 is B. 7, let's compute the determinant of this matrix here. So whenever you get something like this, we're really looking for rows or columns that have only one value in them. And we can use our nifty plus, minus, plus, minus, plus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. It's a little much in this case, but it'll be helpful, and you'll see why in a second. Because we can take the determinant of this entire thing just to be the determinant of -3 multiplied by the sign for -3's position in this 5 by 5 matrix. And we can multiply that by the determinant of the matrix that's left when we cross out the row and column that -3 are in. So we'll have -3, and then we have to multiply by -1, because that's its position in this nice little guide matrix over here. And we are left with, well, what are we left with? Let's cross these out. We're left with the determinant of 0, 0, 1, 3, 3, 3, 2, 2, 0, 0, 2, 2, and 0, 5, 3, 4. And now the cool thing is we can do this again. So we still have our factor of 3, but now we have a 3 in this position, which corresponds to, whoops, that's the eraser, corresponds to another negative sign there. And so we can take this 3, bring it out with its negative sign, and multiply it by the matrix that we're left with when we cross out the columns that that 3 is in. And that leaves us with 0, 0, 5, 1, 2, 3, 3, 2, 4. And I bet you can see where this is going. We can expand this even further, and we'll have 3 times negative 3 times, we'll pull out this 5, and its position, its position in a 3 by 3 matrix, which is just this section, is a positive sign. So we don't need to add anything there. And we are multiplying by the determinant of 1, 2, 3, 2, which is negative 4. Yes, negative 4. Okay, thought I messed that up for a second. So negative 4. And when we multiply all of this out, we are going to get 180. So 7 is D. I remember being very scared of this matrix during exam 1, looking through this exam, trying to solve it by, putting it into upper triangular form. But a lot of the time, especially if you're seeing lots of nicely placed zeros all over the place, often this method is the way to go. Question 8, if the determinant of this matrix here is negative 16, what is the determinant of this? So pretty much we're going to have to apply the rules that we know about the properties of determinants under different row operations, and we'll be able to figure out what it will take to take this determinant of negative 16, apply a bunch of things to this matrix, and turn it into this, and we'll be able to keep track of the determinant as we go. So right off the bat, we know that adding a factor of a row to another row does absolutely nothing. So adding 6c here is no good. That will not change our determinant at all. So we can cross that off, and our determinant is still negative 16. Next thing we can do is cross off these 2's, and we know that multiplying a row or a column by a factor will multiply the determinant by that factor. So crossing off that 2, we will have to divide by 1/2. Next, we see that a column and a row have been multiplied by -1, as in this column right here, that row right there, and this column right here. And so overall, that will multiply our determinant by -1 twice to get rid of those. And so overall, nothing actually happens as a result of that. And then finally, what else? Let's see, what else do we have to do? Well, it looks like we're going to have to transpose. Yes, we're going to have to transpose our matrix because we want C1, C2, and C3 to go down the third column there. So let's transpose this. We're left with C1, C2, C3, A1, A2, A3, B1, B2, B3. And remember, at this point, this matrix here corresponds with this determinant. Right now, we're sitting at -8. Now, what do we have to do to get this into this form as we see here? Well, all of our columns are out of place. We're going to have to flip these two, switch the places of these two. Now we have C in the middle, and then we're going to have to exchange C with B. And so doing two flips like that will each multiply our determinant by -1 again. So yet again, just like crossing out the two factors of -1 like we did up here, 2 column flips will do nothing to our determinant. So this, in fact, is the determinant of this guy right here, which is just -8. So 8 is E. 10. Which of the following sets of vectors are subspaces of R3? We're going to do these really quickly and completely geometrically. We don't need to do anything else other than think about what these things are. What we're looking for is a line that passes through the origin. In fact, a point on the origin would also work. a plane that passes through the origin, or well, actually looking at these options, yeah, those are the only three that we're really testing for here. So 1, what is option 1? Well, option 1, it doesn't matter whether or not you can really figure out what this guy looks like. In fact, this is the coordinate planes. This will graph out as a coordinate plane. So if we have x, y, z, this would be the yz plane, the xc plane, and the zx plane, because one component or more at all times must be equal to 0 for that condition to be true. And we see that if we have a vector in two vectors in different planes, if we add them together, they will kind of jump out of either of the planes, and they will have a non-zero value for all three components, and so we're not closed under vector addition. Because really what we're testing here is closure under vector addition, scalar multiplication, and inclusion of the 0 vector. So 1 does not work because it's not closed under vector addition. 2, the set of all vectors satisfying this condition right here. Well, we can save some time. In a final situation, you'd really want to be able to go through these relatively quickly, and we see that, in fact, this is a plane that passes through the origin. We know it's a plane because we can plug in 0 to x, y, and z as and the condition will remain true. So 2 is good. What about 3? Well, that is just the origin. That is a circle of radius 0 at the origin, and because if we take any vectors that are the origin and add them to another vector at the origin, we're going to stay at the origin. So we fulfill vector addition. We also fulfill scalar multiplication because there are no non-zero factors by which you can scale the origin to get out of the origin, and obviously we include the origin if you didn't get that before. Okay, so 3 is good. What about 4? The set of all vectors satisfying that condition. Well, does that have the 0 vector in it? It does not. If we plug in x equals 0, y equals 0, and z equals 0, we get 0 equals 1, which is a contradiction. So 4 is not closed under, well, it's not closed under vector addition. It's also not closed under, sorry, it doesn't have the 0 vector. It's not a closure thing. Okay, and 5, the set of all vectors satisfying the condition x equals y. Well, this is just going to be a plane. We can graph it out, but you'll see pretty quickly x, y, z, that this is a plane. Oh, I should have really changed this, but it's a plane, passing through the origin and unbounded on z, so it's going down and up through the paper there. And it does pass through the origin. It's a flat plane, and so it satisfies all of these conditions. So 2, 3, and 5. 2, 3, and 5 work. So 10 is C. 13, which of the following values is a multiple eigenvalue of A? So I messed up my algebra and got stuck on this one for a good long while, so hopefully it doesn't happen to us this time. We can find the determinant of this by substituting, well, the determinant of A minus lambda I is really what we're solving, but we're doing that by substituting a negative lambda in at all of these positions and finding the determinant. So we can express this determinant as 2 minus lambda multiplied by the determinant of this submatrix, which is negative 1 minus lambda multiplied by the determinant of this submatrix, which is negative 2 minus lambda multiplied by 5 minus lambda plus 6. And then we need to close out all of these parentheses. And it was a parenthesis mistake that I made last time, and you'll see why it's pretty important in just a second. So solving this whole thing, you would think that we would need to expand everything out and refactor it, but we actually don't. We can skip that step. We can just see that this is equal to 0 when over here when lambda is equal to 2, here when lambda is equal to -1. So now we have to be careful, because when we come to this last half, we're going to have to expand it and refactor. And it's actually a lot easier than you'd expect. We'll have lambda squared minus 5 lambda plus 2, so minus 3 lambda, minus 10 plus 6, so minus 4, and this whole thing has to be equal to 0 for this entire expression to be equal to 0. This will factor to lambda plus 1, lambda minus 4. So we'll see that lambda is equal to 4 in this case, and lambda is equal to -1 here. And we see that our multiple eigenvalue is lambda equals -1 because it has a multiplicity of 2. So 13. 13 is A. Okay, 15. Let A equal 1, 1, 0, 2. What is A to the 6th power? A to the 6th power. We're going to be using the fact that A to the 6th is equal to P d P inverse for the diagonal matrix D, which encodes the eigenvalues of A, and then some matrix P, which will be the eigenvectors corresponding to the eigenvalues encoded by the columns of D. So let's and sorry, I messed this up. This is D to the 6th, and this is really a general case that A to the K is P d to the K P inverse. But in this case, we're solving for this guy. So let's find our eigenvalues and eigenvectors of A. Since A is an upper triangular matrix, its eigenvalues are just equal to the elements of the upper diagonal. So lambda is equal to 1, and lambda is equal to 2. When lambda is equal to 1, our matrix is 0, 1, 0, 1, and the corresponding eigenvector for this matrix, since x1 is free, is 1, 0. And secondly, when lambda is equal to 2, our corresponding matrix is -1, 1, 0, 0, and the corresponding eigenvector for this is 1, 1. And so we can form this whole section right here and get ready to compute it. Our matrix D is going to have our elements of lambda, so lambda 1 and lambda 2, on the upper diagonal so that it's a diagonal matrix. So we could put the 2 first, but I'm going to put the 1 first. It does not matter. 1, 0, 0, 2. But what does matter is that the rest of everything follows along in the same way. So the eigenvector corresponding with 1 will have to go on the left of our matrix P. So our matrix P is 1, 0, and 1, 1. Now finding P inverse is pretty easy. We have to switch the A and D position, so we're still left with 1, 1, and then we have to negate the B and C positions, so 0, -1, and then dividing by the determinant is just dividing by 1, so we don't have to do much there. And if we solve this, see what this is equal to, we will have our answer, but I got to be careful. I keep dropping the 6. We have to take this to the 6th power, and this will be just 64 there. So taking our first operation here, because remember we compute these right to left, we are going to get, and actually I'm going to copy this. Copy this over. Okay, we're going to get another 2 by 2 matrix, and it's going to be composed of 1, 0, -1, 64. And as our final step, I'm going to go in and remove all of this, duplicate this over, and we will be able to solve for our final 2 by 2 matrix, which will be composed of 1, 0, -1 plus 64, oh, sorry, not negative 63, 63, and finally 64. And that is option D, 15. 15 is in fact D. 16, which of the following matrices are diagonalizable? Believe it or not, we can do about half of this question in, I'd say about 5 seconds, because an important fact to just have in your arsenal of matrix facts, of which we need many, is that all symmetric matrices are diagonalizable. So 2 is a symmetric matrix because it is equal to its own transpose. You can test that out for yourself, but really I'm just looking for a mirror image down the main diagonal. So everything on either side of the main diagonal is the same. So this position is the same as this position, this is the same as this, and this is the same as this. And you'll probably already see it. 4 is in fact also diagonalizable. So 2 and 3 must be correct. So anything that doesn't include 2 and 3 is already out of here. Okay, what about 1? Is 1 diagonalizable? Well, we're actually going to have to solve for this ourselves. We're going to have 1 minus lambda, -2 minus lambda, minus 4 is equal to 0. And expanding this out, we'll have lambda squared plus lambda minus 2 minus 4 is -6 is equal to 0. This will be lambda plus 3, lambda minus 2, or lambda is equal to -3 and 2. When lambda is equal to 3, lambda equals 3, the corresponding matrix that we get by plugging in, lambda equals -3. When we plug that in, we will get 4, 4, 1, 1, which is equivalent to 1, 1, 0, 0. And so the corresponding eigenvector for this will be -1, 1. And then finally, if lambda is equal to 2, we are going to get -1, 4, 1, -4, which is the same thing as 1, -4, 0, 0. And so our corresponding eigenvector is 4, 1. And because we have 2 distinct eigenvectors, our eigenvectors can span all of our 2. Thus, this matrix right here is diagonalizable. And in fact, I messed up my crossing things out earlier. These were the 2 options we were between. Sorry if that was confusing. But now we're in a little bit of a sticky situation because we still have to go through and check number 3. So number 3, if we're solving this, we'll be solving, well, actually, because it's an upper triangular matrix, we know that its eigenvalues are going to be just equal to the values on the main diagonal. So that's lambda equals 1, lambda equals 0, and lambda equals 6. When lambda is equal to 1, we are going to be left with 0, 0, 0, 0, 0, 5, 4, -2, 1. And if we simplify this down, we are going to get 0, 1, 0, 0, 0, 1, 0, 0, 0. And because x3 is free, our corresponding eigenvector is 0, 0, 1. And I'll just store this down here. And all we're looking for is for these other 2 to have, like we did before, distinct, unique eigenvectors. Because if we have 3 distinct eigenvectors, 3 linearly independent eigenvectors, we can span all of our 3, and we will be not linearly independent, that too, but diagonalizable is more important than that for us right now. So next, if we take lambda equals 0, we'll have 1, 1, negative 2, 0, 0, 4, 0, 0, 6, which is equivalent, row equivalent to 1, 1, 0, 0, 0, 1, 0, 0, 0, where x2 is free. And so we will see that we get a vector negative 1, 1, 0 out of that. And now finally for lambda equals 6, we will end up with negative 5, 1, negative 2, 0, negative 6, 4, 0, 0, 0. And when we simplify this down, let's see, negative 5, 1, negative 2, 0, 3, negative 2, 0, 0, 0. Let's divide this by 3, 6 over 3, and subtract row 2 from row 1. That will give us 0, negative 4 over 3, and yeah, whatever this gives us as an eigenvector, I don't particularly want to solve for it. Right now, it would be a little bit of a pain, but it clearly is going to be an independent, distinct eigenvector from the two that we found before. So if I am correct, all 4 of these matrices are diagonalizable. So 16 should be E, which it is. I was not particularly confident about that. Okay, 17. Consider the dynamical system x prime equals ax, where A is given there. What is the origin? Well, if lambda 1 and lambda 2 are greater than 0, the origin is a repeller. If lambda 1 and lambda 2 are less than 0, the origin is an attractor. If lambda 1 is greater than 0, lambda 2 is less than 0, the origin will be a saddle point. And if lambda 1 and lambda 2 are purely imaginary, then, and really this isn't saying purely imaginary, this is saying they're complex, but you get what I mean. If they're both only composed of factors of I, then the origin is a spiral point. Okay, with these rules in mind, I'm going to shrink them, stick them up here, and let's solve for lambda 1 and lambda 2. We'll be solving 3 minus lambda, negative 3 minus lambda, plus 5 is equal to 0. This will give us lambda squared minus 9 plus 5 is equal to 0, or lambda squared is equal to 4. I'm going a little crazy here. Yes, lambda squared is equal to 4. So lambda is equal to plus or minus 2. And because we have one positive and one negative value for lambda, the origin will be a saddle point. So 17 is C. 18, this is almost our last one. Which of the following is a solution to this differential equation here with initial conditions? So the form that we're going to be solving things into is x of t. I use x of t like how they use x of t in differential equations. It's probably annoying to some of you how they're using two components over here, and one of them is called x of t. But I think we'll all be okay. So x of t is equal to c1 times the eigenvector v1 e to the lambda 1 t plus c2 v2, the second eigenvector corresponding to e to the lambda 2 t. And we can solve for these c1s and c2s using our initial our initial condition here. Okay, going through and solving for all this, we need the eigenvalues and vectors of 2, 3, 3, 2. So we'll be solving 2 minus lambda, 2 minus lambda, minus 9 is equal to 0. This will give us lambda squared minus 4 lambda plus 4 minus 9 is negative 5 is equal to 0. This will give us lambda minus 5, lambda plus 1, and this gives us lambda is equal to 5 and negative 1. And so with this in mind, we can go through and solve for our eigenvectors. So if lambda is equal to 5, we will be left with negative 3, 3, 3, negative 3 as our matrix A, which will simplify down to 1, negative 1, 0, 0, which gives us the eigenvector 1, 1. If lambda is equal to negative 1, we will have 3, 3, 3, 3 as our matrix A, which simplifies down to 1, 1, 0, 0, giving us the vector negative 1, 1. And so we can already put together a lot of our solution x of t. And in fact, yeah, we're ready to solve for our initial condition. So if our initial condition is 2, 4, 2, 4 is going to be equal to C1 multiplied by our first eigenvector, which is 1, 1, times e to the lambda 1, which is 5, times 0, plus C2 times negative 1, 1, e to the negative lambda t, where t in this case is also 0. And when I said lambda, I meant 1. And so because both of these e terms will go right to 0, we can solve this as a matrix, as an augmented matrix, 1, 1, negative 1, 1, and all that's equal to 2, 4. And so simplifying things a little bit, let's subtract row 1 from row 2. We'll have 1, negative 1, 2, 0, 2, 2. We can simplify this down further to 1, 1 here. Add row 2 to row 1, 0, 3. And we have our values for C1 and C2. C1 is equal to 3. I'll replace this with a t. And C2 is equal to 1. And we are done. We should be able to match, well, this isn't true anymore. This is x of t. It's even bugging me. Okay, I'll do it the right way. X of t, y of t. I need a better name for it. So we're looking for 3e to the 5t. We agree with that. And then in our second component, we want a negative first term. And so c is our correct answer. What was that? 19? No, that was 18. 18c. Which it is. Nice. Good, good, good. Okay, let A equal this guy, and we are trying to figure out what eigenvalue this complex eigenvector corresponds with. So solving the determinant of A minus lambda I will give us lambda squared plus 16 is equal to 0, so lambda is equal to plus or minus 4i. 4i. If lambda is equal to 4i, let's just try that one first, then we'll be left with the lambda equals 4i. We'll be left with the matrix minus 4i minus 4i minus 4, 4. So from here, we can take this, I don't know, let's go with the second line here and take that and set it up as an equation. This is saying that negative 4 x1 minus 4i x2 is equal to 0. And we can solve this and simplify it a little bit more by saying that negative x1 is equal to I x2, and we'll switch the sides of that negative sign there. And now this is actually looking pretty good. We can express this solution in terms of x2 if x2 is a free variable. x1 is equal to negative I x2, and x2 is equal to 1 of itself. So we see that this, in fact, is our corresponding eigenvector, and it corresponds to our eigenvalue of 4i, and it matches up here. So B is our correct answer for 19. What else do we have to do here? Okay, we have a very simple invertibility diagonalizability question. Here's a good question for you. Does invertibility ever imply diagonalizability? Does diagonalizability ever imply invertibility? The answer to both is no. They have absolutely nothing to do with each other. You can never assume one because of the other. In this case, it's obviously an invertible matrix because our determinant is 25. You can just see that at this point. Hopefully you should be able to. And then we're getting some hints that it could be non-diagonalizable because we are going to have lambda equals 5 with a multiplicity of 2. And remember, I'm getting that because A is an upper triangular matrix, and if that's the case, then our values for lambda are just the entries of that main diagonal, like we keep saying. So if lambda is equal to 5, for lambda equal to 5, our matrix will become 0, 0, 0, 1. And the corresponding eigenvector for this is 1, 0. And because we only get one vector, we would need 2 vectors to span all of R2, 2 distinct eigenvectors to span R2. And since we don't, we cannot span R2 with our eigenvectors, so we are not diagonalizable. Okay, so A is invertible, but not diagonalizable. 21 is B. And I believe, yes, that is it. Okay. Have a nice day, I guess.